Today we're going to be looking at some of the graphs that you may encounter in terms of distance, velocity, and acceleration, and even some definitions of acceleration and calculations that way. So let's say I had a straight line distance versus time graph. So that just means that I have distance on my y-axis, time on my x, seconds, distance in meters. And let's say I just had a graph that looks something like this. First thing you need to understand is the gradient. What does a gradient represent in the distance versus time graph? We know that gradient is the change in y over change in x, and in this case that is the distance over time. And we know what distance over time is. It's your speed. So the gradient in this case gives you your speed. So from A to B, you can see there's a straight line. And a straight line means constant gradient. The gradient of this part is the same. So you have constant gradient. And we know that constant gradient or gradient refers to speed. So therefore, you have a constant speed. You can see between points B and C, you have zero gradient. So that means that you have zero speed. In other words, you're not moving. And then from point C to D, you can see once again you have constant speed. Now that's quite simple. So how about we look at some curved distance versus time graphs. Now in this case, you can see between A and B, you have increasing gradient. You can see that the gradient goes higher and higher. And we know that the gradient in a distance time graph refers to the speed. So this means you have increasing speed. Now if you look at points B to C, you can see that the gradient is decreasing. Gradient. So that means the speed is decreasing. If you look at points C to D, you have zero gradient and therefore zero speed. Now just a quick thing on terminology, increasing speed can also be denoted as accelerating, and decreasing speed can be noted as decelerating. Notice how accelerating or decelerating is with reference to whether the speed is increasing or decreasing, not the acceleration. Let's say I wanted to find the velocity at point B and the instantaneous velocity at point B. The way I do this is I would have to draw a tangent at point B. So it could look something like, point B is a bit difficult because it's on a point of inflection, if you know what that is. But you try to draw a tangent there, and you work out the gradient of that tangent. So to find instantaneous velocity or instantaneous speed, draw tangent at the point and work out gradient. Okay, so now let's look at the straight line velocity versus time graph. If I wanted to find out what the gradient of a line or whatever represents in this graph, we do the same thing. So gradient is change in y over change in x, which is velocity, change in velocity over change in time, and that gives you your acceleration. So the gradient represents your acceleration. If you look at points A to B, you have constant positive gradient, so it means you have constant acceleration. B to C, zero gradient, and that means you have zero acceleration. And what that means is you also have a constant speed. If you have zero acceleration, that means you have constant speed, or I should say constant velocity. C to D you have constant acceleration again because of the constant positive gradient, and from points D to E you have a constant negative gradient, and that means that you have constant deceleration, slowing down. So now we looked at what the gradient represents. Now let's look at what the area under the graph represents. So if we split this graph up into segments, let's call these segments A, B, C, D. Now the area is basically the y-axis times the x-axis. So if you wanted to find what the area represents, you do the velocity times by the time. And we know that velocity times time is displacement. If you wanted to find out the total displacement from the starting point to the whatever it is, a car or cycle, whatever is being represented here, it's the end point of its journey, you'd find the total area. So the displacement, overall displacement, is equal to total area, and that would be equal to A plus B plus C plus D. Now if I'm quickly going to draw another graph. Now, if you worked out all the areas of A, B, C and D, here's where the difference between distance and displacement comes into play. We know that distance is a scalar, and we know displacement is a vector. Distance has magnitude only, so you're adding the total distance it travels. So you're adding up all the areas. It travels a total distance of A plus B plus C plus D. Now displacement is the straight line distance from its starting point to its end point. If you looked at how this vehicle was travelling in terms of distance or displacement, in this section here, it's moving with positive velocity, which means it's moving away from a point. And then when the velocity at this point goes negative, it means it's coming back. So when it's measuring distance, you're measuring the distance there and there to this point. But when you're measuring displacement, you're only measuring this point there. So your displacement is A plus B plus C minus D. Because it's negative, because that area is under the graph, to work out the displacement, you subtract it from the others. So let's look at a curved velocity time graph now. So from points A to B, you can see that the gradient is increasing. And we know that gradient represents acceleration. So that means that you have increasing acceleration. And what that means in terms of the velocity is that the rate of increase in velocity is going up. So that means that the rate of increase in velocity is increasing. From points B to C, you can see that we have the gradient as decreasing. And what that means is we have decreasing acceleration. Now, this can be a little confusing. Notice that the gradient is going down, which means that the acceleration is going down. However, the gradient is still positive. If you drew a tangent at any of these points and you worked out the gradient would be positive. That means that the acceleration is still positive. So the car or the body is still speeding up. The velocity is still increasing. It's just doing so at a slower rate. The acceleration is still positive, but just not as big as it was at point B. So it's still speeding up, but just at a slower rate. So you can say that the rate of increase in velocity is decreasing. We know at points C to D there's zero gradient, and we said before that's constant velocity, and at points D to E there's constant deceleration. Let's look at acceleration. Acceleration, the definition for acceleration is the rate of change in velocity with respect to time. So what that means is you have acceleration is equal to change in velocity. That delta sign means changing over time. We know velocity is a vector. We know time is a scalar. And here's a little trick that you can use to determine whether a quantity is a vector or scalar. If you have a vector multiplied or divided by another vector, you get a scalar. If you get a scalar times a scalar, you get a scalar. But if you get a vector times a scalar, you get a vector. So you can almost assume that vectors are a negative quantity, scalars are a positive quantity. So if you times a negative number by a negative number, you get a positive number. Positive by positive, you get positive. And a positive by negative, you get negative. So this means that acceleration has both magnitude and direction. We can rewrite this equation as acceleration, a, is equal to the change in velocity, which is the final velocity, v, so v is the final velocity, minus the initial velocity, which is u, and you can divide that by time. And that will give you the average acceleration between the starting velocity and the final velocity. I'm going to give you an example now. Let's say I had a car, and it's moving around this roundabout, okay? Around the roundabout. And the car is moving at 15 miles per hour constantly. So it's moving at the same speed the whole way through. Is the car accelerating? Quickly pause this video and have a little think about your answer. So hopefully you've had a think now. We know that acceleration is equal to change in velocity over time. Now, it's moving at 15 miles per hour, so the speed is not changing. The speed is constant. However, remember that velocity is both direction and magnitude. The speed is the magnitude of the velocity. So the magnitude is not changing. But you can clearly see that as this car goes round the roundabout, the direction of velocity is always tangential to the circle. So you can see the direction of the way the car is moving is always changing. So you know that because velocity is both direction and magnitude, you know that the direction is changing even though speed is constant. Since velocity is dependent on both direction and magnitude, the velocity is changing. And therefore, because the velocity is changing, you know that change in velocity over time is acceleration. The car is accelerating. You can quote this equation, A is equal to change in v time. So if a question like that comes up in your exam, remember that if a body is moving around in a circle at constant speed, it is still accelerating. Now, the best piece of advice I can give you after watching that video is to go off and practice some past papers or topic questions. These are single-handedly the best way to help you commit the content you've learned to memory. Obviously, go and do all the YouTube stuff of liking, subscribing, And if you found this video helpful, feel free to go and watch any of my other ones.